GRChombo for GRChombo for GPU generation. And I'm sorry for misspelling the name again.
No, no. So
Uh,
actually, I have to. Yeah, that was entirely my fault, Rahimi. So I actually, for some reason, I can't type the name of our new code. I always get the the letters in the wrong order. So it is entirely my fault. I keep doing it, and yeah. So it is GRTeclyn, is the correct. So I've got it correct on these slides, fortunately. So yeah,
Thank you very much.
thanks. Okay, I'll get started. So yeah, I'm always very happy to come and talk at the Einstein Toolkit meeting. So yeah, this is a talk about another code that's not part of the Einstein Toolkit, just to be clear. But we're good friends, and therefore we always like to share what we're doing. And we have in the past learned a lot from each other, and hopefully we'll continue to do so in the future. Um, okay. Let me start by saying what's this thing GRChombo, because maybe you don't know about our existing code, which is called GRChombo. So as I say, we're a good friend of the Einstein Toolkit. I always have to say thanks to our Einstein Toolkit friends, especially Ian Hawke, Uli Sperhake, and Helvi Wittek. So we actually started out on this project during my PhD back in 2013 now. And we were a new code. So on this slide, it says a new AMR-based open source code. And I start to feel kind of old now because we're not new anymore. We're actually quite long-lived. But at the time when we started out, we had really a lot of help from the Einstein Toolkit, people telling us, giving us example waveforms that we could check whether we had things working correctly, giving us tips, all the things that you don't find in papers. So, if you ever go and write your own numerical relativity code, which I absolutely think you should not do, despite the fact that we did it, you always need help from people because there's so many kind of tips and tricks that are, as I say, not obvious in the literature. Um, so, yeah, we're a relatively small code, definitely relative to the Einstein toolkit. Um, so that's an advantage, a good thing and a bad thing. So this is where we have one repository, GRChombo, in GitHub, and so I can fit the source folders, and the examples that we have on sort of one page, which shows kind of how small we are. So we only have these four examples, which are relatively simple. And we're, binary black hole, Kerr black hole, some stuff with scalar fields. And we would like to expand this, but we always are very fussy about what goes into the code. So this tends to make it very slow in terms of updating things, and in terms of getting new features and new examples into our public repository. And this has also stalled a little bit because of what I'm going to talk about later, because of the fact that we're now focused on kind of upgrading or porting GRChombo to a new framework. But one of the things that's been, I think, an advantage for us is that because we're quite small, porting this code to a new underlying framework has been much easier than I think it has been for the Einstein toolkit. So knowing how difficult it's been for us, thinking about how hard it's been must be for the Einstein toolkit, I have a lot of sympathy and respect for Roland and Eric, and all they were talking about yesterday. Okay, so yeah, what I said we're GRChombo, so we're actually built on top of this Chombo library. This is where the name comes from. So this is a set of libraries developed at Lawrence Berkeley National Labs in the US. And at the time when we were doing this project, this was one of the main libraries for solving partial differential equations with adaptive mesh. So it was also sort of focused on fluid applications, and we thought that this would be a really good set of libraries on which to build a new numerical relativity solver that could do this kind of fully adaptive mesh. So not just box within box for a couple of compact objects. Um, so since then, Chombo has sort of stopped being so developed. So there was a kind of a battle in the US. I don't know how to describe it. And between different libraries like this, and AMRX won essentially. So Chombo and AMRX share a kind of common parentage in BoxLib. And in the end, it was AMRX that got a huge amount of funding and went on to develop more. And kind of sadly for us, Chombo didn't. So Chombo itself still has some updates, but it's kind of definitely a lot less active than AMRX. So, why did we want this adaptive mesh? So we really wanted it because we tend to focus on problems that aren't the sort of standard binary black hole problem. So in particular, I was working with Eugene Lim, who wanted to do bubble collisions in cosmology. Pau Figueres, who's at Queen Mary as well, was interested in doing these higher dimensional black holes that tend to have a kind of ring or disk-like structure. And so for these things, you can't just use a box, box within boxes, or you can, but then you would be very wasteful in a lot of the domain. So you want to have things like I'm showing in this picture, where you're sort of zooming in on where, for example, the scalar field has some gradients, or other regions where you essentially need more resolution. And then you can save a bit by in the middle, you can kind of zoom out again where you have less resolution. So yeah, we do other things. So yeah, as I say, one of the main drivers was cosmology. So in cosmology, you can have sort of black holes or overdensities forming in kind of random locations that you don't know ahead of time. So you want to be able to adapt to that, and add resolution dynamically during the evolution. Another fun thing that I did with our code is warp drives. So I looked at if you have the Alcubierre metric, and then you let the kind of the fluid collapse. You generate gravitational waves from that. So, important applications in detecting aliens in the future. So yeah, as I say, we generally do things that are kind of beyond sort of the astrophysical applications of numerical relativity. And so this ability to use adaptive mesh has been really important for that. So we can also do black holes. You can see here that the grids are not sort of box within box. So I'll come back to this a little bit, but actually, when I look at this, so this is one of the first simulations I actually did during my PhD, when I finally got it working and could evolve black holes. And I actually, I look at this now and I think this is sort of catastrophic because you can see that there's a lot of corners, and a lot of kind of grid boundaries are quite close together. This probably gives you a very noisy evolution that's not very good. So I'll come back to saying a little bit more about the sort of the pain of adaptive mesh later. But in general, this kind of regridding, although it's very flexible and very nice, you have to take some care with how you do it. And probably in this scenario, just sort of box within box might be more efficient. The nice thing is that because it's fully adaptive, it's just as easy to do 3 black holes as it is to do 2 black holes. Once I'd run this simulation of 2 black holes, my supervisor Eugene Lim got very excited and said, "Do 3 black holes." And then I did 3 black holes, and then he said, "Do 10 black holes." So I mean, I couldn't find the picture of the 10 black holes, but it's somewhere. And it's very silly. It certainly isn't very well converged, but the sort of the principle was that we could now do sort of multiple black holes with the same code, and so that is one nice aspect of it. Okay, so yeah, Einstein Toolkit now have adaptive mesh refinement with Carpet X. So I guess I should say if I have any advice for you, and we have a lot of advice, but as I say, a lot of it's not really good news. We have this, our sales pitch is, oh, we've got adaptive mesh refinement. That's really exciting. That's great. But of course, with great power comes great responsibility. And so there are always, problems for every kind of improvement that you have. So this paper we mentioned yesterday, Mirin Radia sort of led this. He is now a research software engineer in Cambridge, but he was at the time a PhD student working on the code. And I think it is a useful paper because we just wanted to sort of share the sort of the issues that we'd had and what we'd found that works and what we'd found that didn't work. So I do refer people to this for sort of the tips that no one ever tells you. We tried to be fairly honest about things. Um, so I'll summarize some of the main things. So one of the main things, and it's kind of obvious, but you should never do this, right? So where, this circle is supposed to represent either a black hole horizon or some blob of matter with some steep gradients here. And you should always make sure that you have the boundary of this object or the black hole horizon on a single grid. Um, so, you know, you might think, having used carpet, well, why would you ever come up with this weird scenario? But this is something that's relatively common when you use adaptive mesh refinement, because what happens is you go through and kind of tick all of the coarse boxes that you want to be refined. And then you kind of decide which regions to refine, but you don't refine every cell that you tick necessarily, because maybe there's just one cell on its own over here that's ticked. Do you want to put a refinement box around that? Your refinement box will probably need to be something like at least 8 by 8 in order to make it worth creating a new patch there. So we typically have like 8 by 8 or 16 by 16 boxes. So if it happens that, your 16 by 16 box ends, at this boundary, just because it's refining all over here already, then sometimes these edge cells will just not get refined, right? And you have to kind of force it to sort of, in a way, over tick where it wants to refine. So you can add kind of buffers to where you designate for refinement to try and push the boundaries out further and make sure that it does refine the whole thing that you're interested in and doesn't kind of cut off a corner. So yeah, in that sense, if you use the kind of, if you tick in boxes, then you just have to make sure that your boxes are in kind of multiples of whatever this regridding box size is that you use in the adaptive mesh, so that you always get sort of whole boxes refined. So this is just something that, as I say, is always a bit painful. Um, Also, so I asked Roland yesterday about, so what criteria are you using for refinement? Because it's amazing that you kind of think it will just be obvious what you should pick. You think, oh well, I know, I have some stuff here and some stuff here. I can just maybe use the density and regrid according to the density, and that will give me some nice refinement in the right place. And it turns out that actually that kind of simple way of tagging often just doesn't work. And I've never completely understood why that's the case, but what I would say is often, especially in the Einstein equations, some density can be balanced by it can be balanced by the extrinsic curvature or the intrinsic curvature. So if you just use the intrinsic curvature to try and regrid, but actually all of it's in the extrinsic curvature, you'll not regrid something where actually maybe there is a lot of curvature. So then you can say, okay, well, I'll take something that takes into account all of my variables. And that's probably the best thing to do. But then at the same time, it means your condition for regridding becomes very complicated and requires checking all of the different variables. So it's a kind of trade-off between what's something that's easy to implement and something that actually gives you physically what you want. So I can't remember what I chose for this, but I thought I took the picture of this as, this was something that I thought was very well motivated for doing this problem. And you can see that it seems to be refining areas where nothing's going on, but equally maybe not refining quite enough in regions where it should. And it's, zooming in and out in this space, which is not clear why it should be doing that. So as I say, this is the kind of thing you might see if you try and write your own tagging criteria. So I actually had a lot of discussions recently with David Nilsson when he visited the UK. So David develops the Dendro GR code, and he told me that they have had really good success with this relative error. So this is something we talk about in the adaptive mesh paper. Um, but basically, you have two refinement levels. So you can compare the value of the variable or its derivative on this level and on the sort of less refined level. And if you do that, it gives you some measure of how much difference you're getting from going to a finer resolution. If that's a big difference, it means you probably need more resolution in that region. So you can use that kind of error between levels as a tagging criteria itself. And they have these nice pictures on their website. I don't know if that's what they used here, but you can see here that you're getting this really nice, very even regridding that seems to be following these waves in a very natural way. And so, yeah, David told me that you had to do this for all of the variables, so all of the metric variables, and if you had some, I think scalar fields or something for those as well. You needed to check them all and check their derivatives, and then that gave you something that was really, really robust. So that's something that actually I want to look at in the future for our code. So this is why I said yesterday, I don't know if we're necessarily the best example. We tend to use things that are a bit hacky, that just work, and then we hack them enough so that it gives us the refinement we want. But I think it's something that we can do better. The other thing that you find, of course, is that load balancing is now hard. So when you have a box and a box and a box, you can make sure that this box is double this. So this box is double the size of this box, which means you have exactly the same number of cells on each level for the processors to process. And so if you're using, eight MPI ranks and you have eight boxes on each level, then everything will be nice and it will all be very nicely balanced. But here's an example of one that's really not very well load balanced, where I'm going up to, on the sixth level, I have, thousands of boxes, but on lower levels, I only have several hundred. So if I use 1,000 cores, okay, the top level will go very fast, but then a lot of them will be sitting idle on the lower levels, which is not ideal. Um, so in a way, sometimes there's just no way to get around this. I mean, sometimes you just have to have more, you want more refinement in certain regions, and that ends up giving you more, more cells that you need to process. Um, if that's the case, you really need to focus on load balancing the top levels. So we use this adaptive uh, time stepping that Ian mentioned, where each refinement level kind of takes a different time step. So finer levels take a finer time step. And that means you spend a lot more time on the top levels, the very fine ones. So those are the ones that really dominate your runtime. And so you do want to kind of focus on them when you come to load balancing. Yeah, as I say, for binary black holes, I honestly would just recommend doing a kind of box within box, which you can do with adaptive mesh refinement. You just tag the cells in in within the box that you want to refine. Okay, so you might say, well, okay, why do you need a new code if you already have adaptive mesh refinement? Um, so the main driver for us updating our code from GRChombo to GRTeclyn is the ability to use GPUs. So this was already mentioned yesterday as being a motivation also for the Einstein Toolkit. It is really relevant. So I don't know. Whenever I see people start talking about GPUs, I feel very confused. I mean, I like the physics of what I do, and I'm less into the sort of hardware aspects of computation. I think that's fine and normal, and we're primarily scientists and not computer scientists. So I don't know. This would have helped me when I was starting out, so I just will say it. It never really registered with me that there were actually three kinds of GPU. So I was hearing all of this different language, and I wasn't really understanding why in one sentence they were using different words to in another case. But really, the problem is capitalism in the end. There are three vendors, and they won't agree on any standards or any particular terminology. So they all have their own random terminology for things that are essentially the same. It's very annoying if you go to one of their training sessions because they'll say, oh, this is what CUDA would call X, but we call it, you know, AMDX, right? So they just kind of have all their own languages. And I think this is why it's particularly confusing. So for example, for AMD GPUs, you have to use the ROCm or HIP compiler. For Intel, it's SYCL, and for NVIDIA, it's CUDA. So, when you're used to CPUs, you're just used to, you have a compiler, maybe you use the GNU compiler, and it works on, okay, most systems. Okay, you have some exceptions where you have to use different compilers. But in general, you don't really think about the hardware. You just think, I want to compile this with MPI and maybe OpenMP, and you just go ahead and do it. But once you're using GPUs, you have to be asking, well, what GPU am I using? Therefore, I need to use the right compiler. And okay, they are essentially similar. So they are really just like CUDA, but there are some differences, particularly with the Intel compiler. Okay, so also when you come to run GPU code, it's super confusing. A lot of systems aren't very well set up, in my experience, particularly like Slurm systems are very much designed for submitting CPU jobs and not GPU jobs. So you have to, things are a bit kind of counterintuitive. You have to really remember what the big N and the little n means. So big N, well, at least on this system, this is referring to the CPU node that's running the GPUs. The little n actually is telling you how many GPUs you want to use. You often have this flag exclusive, which you would kind of think if you're using just a few GPUs on a GPU node, you might think that you actually get those and you have all of their memory, but that's not always the case. Sometimes you end up sharing and suddenly your performance will tank for no apparent reason, and it's just because someone else has started using the GPU node. So in general, you really want to take the whole node so that you're really guaranteed to be able to use all of its compute power and all of its memory, especially if you're doing kind of comparison tests. So it's really painful, and I find I always have to ask like the system admins for help, and I always feel really stupid saying like, but what am I actually supposed to put here? So yeah, I just say this to reassure anyone else who's always super confused. So you might say, well, this sounds really painful. Perhaps I will not use GPUs because it sounds very confusing. I'll just stick to CPUs. But unfortunately, you really can't do that. So actually, Eugene, who, as I already said, was my supervisor, was very, very foresighted in this. And I managed to find the email where he said, okay, guys, we need to start working on this. And it was back in 2021. Yeah, he basically said, like, the robots are coming, look out. And this is kind of how we felt about it at the time. Like, oh no, we're going to have to, use GPUs. We don't really have a choice because future systems are going to be GPU based. And I think, we just really had this slightly negative view that GPUs were going to be a pain and they were being forced on us because that's what machine learning people wanted. And that they wouldn't necessarily offer us any advantages, but we just had to have a code that would run on them because otherwise we wouldn't be able to run our code anywhere and we would be out of business. So that was the motivation for sort of starting to develop GRTeclyn. I mean, you can see that this was sort of 5 years ago. So it's taken a really long, I mean, we haven't been at first we were sort of just investigating different options. And we've only really started to focus on it in the last few years. But it's definitely, this foresight that Eugene had has been correct. We really, the next generation of computing resources, at least in the UK, will almost certainly be mainly GPUs. So we can't avoid this. But I think, it is also an opportunity. We're moving into this era of precision gravitational wave science. And so, maybe these tools can help us to do better. And I now actually think that they can, whereas I was incredibly cynical initially. So, okay, this is a very hand wavy discussion of GPUs. But I think it's always helpful just to understand like why are they so much faster? Like, why are they really helping us? Why is it a kind of a step change in how you can process things? So in our standard kind of MPI picture, you have one CPU that works on one area of your grid, and it goes sequentially through the points, right? It processes one point at a time. Maybe it's calculating the right-hand side of the Einstein equation at each point. It will calculate each one and then, store it back on the grid. Whereas with GPUs, you take basically you can actually take the whole grid, right? Well, you do each level in turn. So where you have multiple refinement levels, they are always in serial, right? They are never parallelized for the moment. There's ideas about how to do that. But especially where you have the adaptive time stepping, you can't do that. But you can take every level, right? And you can just feed the whole thing into one GPU, get it to calculate the right-hand side everywhere, and then stick it back into memory. So in one kind of clock cycle, you're doing all of the calculations for the whole grid, as opposed to working kind of sequentially through the points. Um, so, this shows you why potentially you can have a lot better speed up. Of course, then you still probably want to use some MPI, right? You still probably want to share the grid. If your grid is really big and you have lots of points, you can then, there's a limit to how much one GPU can process based on really on its memory bandwidth, right? How much memory it has. So you probably will still end up splitting the grid, but into very big chunks, right? Compared to your MPI chunks. So on in our code, we often have each sort of box that's worked on by each rank being something like 8 by 8, so sorry, 8 cubed or 16 cubed. But it needs to be a lot bigger to fill the GPU. You want to sort of fill it as much as possible. Um, so yeah, I think this is common to most codes. Most codes in numerical relativity are upgrading or consolidating. And yeah, this is the case for us. Our old code GRChombo is now becoming GRTeclyn. And we had to rebrand ourselves. So I think we'll always be known as the GRChombo people. But we now have this name, the GRTL collaboration, which I think is general relativity testing the limits or something like this. Um, but it depends who you ask. So yeah, we kind of had to rebrand, but I think we'll always be the GRChombo people. Okay, so what is GRTeclyn? GRTeclyn means tool. So Teclyn means tool in Welsh. Um, Chombo meant tool in Swahili, so we kind of kept the GR plus a word that means tool in a random language theme. And we have that for some of our other codes. So this was one of our meetings where we all had ideas for code names and we stuck them up on a board. And GRTeclyn kind of won, mainly just because we couldn't think of any other really good ideas, or they turned out to sound rude, or were offensive in some other language that someone knew. So GRTeclyn was just kind of the one that wasn't the worst. Yeah, but I think it's an okay name and it's easy to Google, which is very important. So for us, it's an almost straight swap of GRChombo for AMRX, which is a good thing. So as I said earlier, these codes share a common origin. So actually, a lot of the code in Chombo looks very like the code in AMRX. So that was really lucky for us. That's made it quite easy. So since we use AMRX, that actually makes all the GPU magic happen. So one of the nice things is it's all in AMRX, all of the GPU stuff that allows it to work on these three vendors. And you just have to tell AMRX when you compile it which one you're using. So if I'm using the AMD GPU nodes, I tell it to use HIP, which is the compiler for AMD nodes. I have to give it this architecture code, but you can Google these. They're relatively easy to find. And this is kind of all I need to give AMRX, and then it will just go and generate the code. It will go and compile the code that's appropriate for this system without me having to do much more. So AMRX definitely gets all the credit for doing the kind of clever GPU stuff. Um, So yeah, just to show you kind of how minimal the changes are in our code, this is where we implement the right-hand side of the Einstein equations. So on the left is GRChombo and on the right is GRTeclyn. And so I guess particularly if you look at this part at the bottom, we had this structure. So we had this thing called box loops, right? Box loops loop would go and apply this class, the CCZ4 right-hand side class, to all of the cells in the grid. It would have the solution at the current time and it would work out the right-hand side. Um, so that now in AMRX is replaced by this AMRX parallel 4 kind of structure where you give it again the right hand side, which is what you want to write out, and you have this lambda function. So it goes over all the boxes, over all the cells, and it applies again this CCZ4 right hand side. And so most of what's in this class, the CCZ4 right hand side class, hasn't changed much between these two um, uh, in this upgrade. So it's really, for a user, from a user perspective, it's quite an easy change. You just, wherever you have a box loops, you now have this AMRX parallel 4. And AMRX parallel 4 will make sure that it runs on the GPU in the correct way. And then, yeah, within the classes that then are called by this parallel 4, you have to specify this AMRX GPU device. So basically telling it that when you're using GPUs, so this code still works on CPUs, but when you use it on GPUs, this tells it that this is the thing, this thing should be something that's run on the GPU. And you want to force it inline. So this was discussed a bit yesterday about how you want to kind of inline functions that go on the GPU. Um, uh, so yeah, so we also had an opportunity to tidy up. So I actually think that the new code is simpler than the old code. So if you look on the left, we had this horrible thing. So there's historical reasons for everything. In GRChombo, we had explicit vectorization. So we were actually trying to turn CPUs into GPUs by making them process chunks of the grid all in one go. And that meant that we had this data T template argument that would allow us to vary the kind of number of points that we processed in any one time. So each point here is not necessarily a point, it can be a vector of points as well. And that vector can vary in length. So we were really kind of trying to do here explicitly what AMRX already does on GPUs sort of under the hood. But it led to horrible code. It led to this code with like templating over, this template type name class vars t. I mean, it's just horrible. Like, what does this even mean? You would just sort of copy it and hope that it still worked. And if there was a problem, like try and, randomly try things to make it work. Whereas now, the only template argument we have, so this is a scalar field, we template it over the potential that the scalar field feels, which is a kind of a logical thing to template the class over. And we don't have any other template arguments like this horrible data T thing. So, we have some structures that we keep the variables in. We keep the first derivatives of the variables, the second derivatives, and the effective derivatives. And this is all, I think, relatively, and then we can access them. Down here, we have the first derivative of chi, where chi is the conformal factor. So, this I think is a lot cleaner and more readable than the previous code. So, yeah, burn GRChombo. This is what I'm really enjoying about the new project more than anything is just the ability to get rid of things that I never liked in the original code. So some other plan changes. So we want to get rid of this horrible explicit vectorization, this data T thing we had. We actually want to get rid of our PETC dependence for the apparent horizon finder. So in general, we find that the more dependencies we have, the more difficult it is to set up on a new system. And that's one of the big barriers for our new PhD students is, they can spend ages just trying to get PETC to work. So we want to try and do something that's using AMRX tools, so we don't have any other dependencies. Simplify the parameter reading. Also, if we can, rely on the AMRX output format. So it does also support HDF5s, but we might try and not rely too much on the HDF5 outputs. We're also using particle methods for diagnostics. Um, we have continuous integration and automated tests, better documentation. So these are all things that are really good, that our software engineers who work with us helped us with. We also have a linter. I don't know if anyone's come across linters. They're really horrible. They basically tell you off when your code has problems in it, but they're really fussy about things that, they will tell you, oh, you can't have this variable name because it doesn't have enough letters in it or something. But it's X. So, X is X, right? X needs to be X. So then you have to put in some exception in the linter to say, don't tell me off for using X as a variable name. But yeah, anyway, I suppose it's a good thing. So yeah,
Katie, you have
yeah.
5 minutes left.
That's perfect. Yeah. So I think I'm almost done. So I guess your main question should be like, is it any good, this new code that you're developing? As I said, we had a lot of help from research software engineers, particularly through the Dirac program in the UK. And yeah, the credit kind of all goes to them. We found that it gives really good results. So this was a picture from a recent hackathon that we went to. This is Juliana, Erica, Miriam, and me. We were a team trying to optimize our code for the AMD GPUs. So this is the CPU time to solution for, I think, just running a few steps of the binary black hole example. And before the hackathon, it was already doing, much better than the CPU, already much faster. And then after the hackathon, we actually managed to get it right down to sort of only to a kind of over 10 times speed up compared to the CPU. And how do we do that? Using AMRX is what gives us the sort of huge advantages, and as I said, they did all the hard work. But things like removing additional structs of variables that we had in the code from Chombo, reducing copying, memory access, removing if statements. So we had an if statement that's like, do you do BSSN or CCZ4? That if statement, just removing that and making it just one or the other at compile time, it gives us a huge speed up just because GPUs don't like kind of branching. Splitting up the right-hand side into several kernels. It's a lot of trial and error. So sometimes you think things will work, but then actually they don't. So you do have to kind of just try things and see what works. Yeah, this is an example of the struct thing that we removed. I won't talk too much about this, but basically we had these kind of structs that we had developed for GRChombo that we thought made it more readable, that we could have a right-hand side object where we could had a member variable for the fields, but now we just write directly into the cell data of MRX, and this gave a big speed up. So the thing that I find most exciting is that we discussed yesterday, it's really hard to do this comparison, right? How do you compare? Do you compare one GPU to one CPU, CPU node to GPU node? Like, what's the right comparison? But if what I really think about is when I did do a binary black hole example, there's a maximum time. There's a maximum speed up that I can get. At some point, I can't parallelize it anymore, even if I have access to a million CPUs, right? I can't scale above a certain level at a certain resolution. And what we find is that if we take that kind of best case scenario in CPUs, it runs at something like 30 M per hour, where M is the code unit. But with GRTeclyn, it's running at sort of 500, 600 M per hour at, just with one GPU node. So something that would have taken 2 weeks on the kind of best case scenario is now taking, potentially a day. which means I will drink a lot less coffee, I think. But yeah, there's a lot left to do. Um, you can see. So I wrote this. I hope to release it in January next year. And then I remembered that I got told off by Mirren on our GitHub, who said we should not put a date. And we shouldn't also call things releases unless we're actually going to do proper GitHub releases. So we had this conversation where I wrote this in our README and then I was made to remove it. So I actually knew Mirren wouldn't like it. But then he got really cross and said, why did you include it in the first place if you knew I wouldn't like it? And I said I was hoping that he just wouldn't notice. So anyway, instead of this sentence, let me say, please refer to this page in our documentation for our code status, and I'll finish and take questions.
Thank you very much, Katie. It was a very informative and nice talk. And I wanted to introduce you at the beginning, but I didn't want to interrupt you. So
Oh, I don't need any introduction. That's fine.
okay.